Hello! Today we will open a new chapter in our exploration of numerical analysis, and the topic is systems of linear equations. Now notice that I didn't say differential equations. I'm talking just about ordinary algebraic linear equations the way we know them from, let's say, from high school. So we already saw systems before, and in high school we typically learn that when the system is a bit larger, then perhaps it may be a good idea to pass into matrix language and use Gaussian elimination. By the way, it's called Gaussian by mistake, but it's another story. Okay, so we know from high school about elimination, and then we enter university. We have our first linear algebra course, and then we revisit systems of linear equations, and we learn lots of structural things, very nice things. For instance, we learn that the set of all solutions is a affine space. We learn how to handle situations where the set of solutions is infinite, things like that. So one would say that, okay, we have the elimination fairly covered. Is there anything else to say? Good question. Well, actually, in real-life applications, the systems that we are handling are special, and the way we are handling is also very specific. Namely, in applications, typically you would meet really huge systems. I'm talking about, let's say, million by million systems. That's definitely not something that you want to do by hand, which brings me to the second important factor. We do elimination using computers. And these two factors, they influence heavily the way elimination works. And therefore, in numerical analysis, we have very good questions. And actually, it will take about 2 lectures to go through them here. So these are really good questions and good answers. And there are some specific things that we have to care about and be careful about. So the numerical version of elimination is somewhat different from the elimination that we learn in high school. So at the start of the first part of this lecture, let me focus just on elimination as a tool. I'm not going to talk about systems yet. Okay? So I have a matrix here, and I will use it to review elimination, because perhaps you are a little bit rusty. So, let's review the basic ideas of elimination. And also let me point out specifics of elimination as a numerical method. So what's the point of elimination? I have a matrix, and my desire is to change it into a specific shape. Let me talk about the shape later on. The important thing is that this elimination is done by stages. We go column by column. And for each column, we have a specific aim in mind. For instance, I start with the first column, and I would like to change it into a form where I have a number on the top and zeros below it. That's what I want to achieve. Now, there are all kinds of operations one can use, because the elimination is fairly versatile. But in numerical analysis, I could say majority of these tricks are actually forbidden. So, for instance, when I was in high school, if I see a matrix like that, I would say, okay, let's divide the first row by 2. But in numerical analysis, this is not really a very good idea, because it would spoil some applications later on. So this is forbidden, okay? Important fact number 1, no division or multiplication of a row by a number in the numerical version of elimination. There are some other tricks. For instance, I could say, okay, I multiply the second row by 2 and subtract the first row, and I get 0 here. Forbidden. Forget about it. There are just 2 operations which are available. And the first operation is connected with my choice of the number in the upper left corner. Now, we will soon see that actually for a computer, there is a certain, let's say, motivation, what kind of number I can see here. And this is called the pivot number, this one, especially after I choose the right one. But for a human being, I would definitely prefer number 1 here on the top. And this brings me to the first permissible operation, which is switching of rows. So my first operation is that I take the second and the first row and switch them around. And I will need it later, so let me mark it using some notation. Now, there is not a, let's say, generally accepted way of marking down operations of elimination, but this one is fairly common. I take row 1 and exchange it for row 2. I think this is fairly intuitive, so yeah, I will stick with this kind of notation. Okay, now this number I really like. And by the way, we will soon see that as a computer, I would not like it, definitely. So that's a slight difference. Anyway, now I would like to create zeros underneath. And for that, we have the second permissible operation. We are allowed to take the pivot row, multiply it by some number, and subtract it from the other rows. And you do it essentially by parallel computing. You just imagine that you have this row as a unit, and you handle it as a unit, but everything is happening in columns simultaneously. So for instance, if I want to achieve 0 here, I can take the number 1 and subtract it twice from number 2, but I do it with the whole row. So I take row number 2, and I subtract double of row number 1, and that will be my new row number 2. Let's go for it. The first row is copied, and I'm taking now numbers in all columns, multiplying them by 2 and subtracting. Yeah? Simultaneous column action. So by 2 subtracted yields 0. By 2 subtracted yields -8. By 2 subtracted yields -2. I actually prefer, when I'm doing it unofficially, to make a little mark here. I'm taking it away twice. And this helps me doing those column operations. Okay, now I need to get 0 here in the last row in the first column. So I look at it and I say, no problem, I take the first row and I add it twice. Okay, I take the first row, multiply it by 2 and add it, and I get 0, 2, 1. And that's the end of the first stage of elimination. I just created the shape that I need here. Some number, the pivot, and zeros underneath. Now, let's have a look at this other operation which I did. I took row 3 and I added double of row 1. Now, this brings me to another of those specifics of the numerical version of elimination. We need to introduce some operations, some notation, and for that purpose, I need to have some, let's say, specific form which I should follow. And the specific form reads that I need to do subtraction here. So if I want to subtract, because that's what the form is forcing me to, I need to think about it as subtracting -2 times row 1. And this will be new row 3. So minus minus gives me plus, so I'm really adding double of row 1, but I have to write it as a subtraction. Now let's have a look at the slide. On this slide, I put some sort of an algorithm for the numerical version of elimination. I call it GEM, which is fairly standard, but not completely standard. And let's not worry about it very much yet as a whole. Right now, we are interested in step number 2, which means that we replace a certain element in the matrix by the element, and I subtract something from the pivot row, some multiple of the pivot row. So this coefficient Lik describes how many times I'm taking away the pivot row. Here we have it. So here I'm subtracting from the second row a multiple of the first row, and I do it, the multiple is 2. And here I'm subtracting from the third row multiple of the first row, and the multiple here, the number, the constant, is -2. And the algorithm comes to this number Lik in the following way. Let's read the first row. So I take a row, k is the number of the column, or the number of the pivot row. So in this case, k equals 1. And I look at i's which are larger, which means I'm looking at the rows which are below. And if I don't see 0 here, which I don't see, then I have to find how many times I should subtract the first row. So how do I get this number 2? I take this number and divide by this number. That's the Lik formula, which we can see over here. Okay? And then we don't actually have to calculate this number, we just know that it will be 0. So I'm just simply putting new Cik to be 0. You can, it's not really a good time to read it in detail now. Let's just follow the main ideas. So this is number 2. Number 2 is this elimination stage. Okay, let's skip step 1 for now. We will get to it later. So that's the first stage of elimination. Let's go to the second stage. After I create the first column so that it looks good to me, I ignore the first column and also the first row because this part is already done. and I move my focus to a submatrix, which is smaller by 1, the dimension, the number of rows, the number of columns is smaller, and I try to do the same thing to this submatrix, which means I look at the first column of the submatrix, the second column of the original matrix, and I try to achieve the shape that I have a number here and 0 underneath, or more zeros if the matrix is really huge. So how do I do it? First of all, as a human being, I don't really like this as a pivot, because if I use it as a pivot, how do I get 0 here? I would have to take the first row and divide by 4 and add. And you can see over here, dividing by 4, I would get fractions. Am I scared? No. But do I enjoy it? No. Okay, let's switch rows. I'm switching row number 2 with row number 3. So what I'm getting is this. 1, 1, 0, and I'm switching now. 0, 2, 1, 0, negative 8, negative 2. Now, as a human being, I like this one much better. This is my new pivot. And I can see that if I multiply it by 4, I can create 0 underneath, which is wonderful. So let's follow the algorithm a little bit. I have my pivot. I take negative 8 divided by 2, and that's negative 4. That's my next L. From the third row, I'll be subtracting the second row negative 4 times. So I will be actually adding 4 times, unofficially. But officially, I have to take row 3 and subtract negative 4 times row 2, and that will be new row 3. Okay, what do I get? I get 1, 1, 0, 0, 2, 1, 0, and I'm multiplying by 4 and, okay, unofficially. You don't see anything here. It's not written here. I didn't do it. 4 by 2 is 8. I add, I get 0. 4 by 1 is 4. I add, I get 2. And that's the outcome of the Gaussian elimination, the numerical version. Only 2 operations allowed. Switching of rows and modifying a row using pivot row. Now, if the matrix were larger, and it need not be square, by the way, then I would simply follow. I would say, okay, the first 2 columns and the first 2 rows are done, and I look at the resulting submatrix, and I keep going like that. So the aim of the numerical elimination is to change matrix into an upper triangular matrix. In general, we will talk about row echelon form, but actually in numerical analysis, in real-life calculations, those matrices that we need are usually based on regular matrices, which means that we always find a non-zero pivot, and we really do get upper triangular matrices. And that's it, nothing more to it. So at the exam, when I ask you to show in an example how to apply an elimination in the numerical way, this is something that I expect to see. Only these 2 operations, no other operations, definitely not, and such an outcome. So that's our new numerical method, elimination, numerical version. And now, as usual, we will start exploring it. And the first question that we always ask is, how about the error of the method? So, okay, let's see. There is some ideal outcome of elimination, the aim, which is the upper triangular matrix. And by how much did we miss our target? The answer is, well, actually, we hit it. So the error of method is none. Now, this is really, really unusual. I think with a little bit of perhaps exaggeration, this is the only numerical method which does not have an error. A little bit of philosophy. Let's go back to integration, numerical integration, quadrature. If you want to get a precise answer, you would have to use infinite division, infinite partition. But we don't have time for that, so we just use finite partition for rectangles, trapezoids, Simpson method. And because we take the essentially infinite procedure and cut it short, we are making an error, the error of the method. When we were looking for roots of functions, let's say the Newton method, and again, if you want to get a precise root, you would have to ask for the Newton method to run for infinite number of iterations, for eternity. But we don't have that kind of time, so we cut it short, And because we took an infinite procedure and cut it short, we are making an error. So this is a common theme in numerical analysis. But this method is actually not infinite. That's the specific part. It's a finite method, because in a finite number of steps, I am actually arriving at the answer. And because there is no infinite procedure which is being cut, it's a finite procedure in its substance, there is no reason to actually make any error. So this is a very special thing. Okay, so we just saved half an hour instead of doing some analysis of errors, things like that. Very nice. So of course, we are not going to talk about order of the method. Nothing like that. We are saving time. Wonderful. So let's ask the second typical question that we ask. How about numerical stability? Because, of course, we are not going to work with such nice matrix in real life. There will be some really ugly numbers, decimal numbers, square root of 2 converted into decimal numbers, outcomes of measurements. So, in fact, there will be some errors in the input matrix, most likely. And then we do operations, more errors. We talked about it. So, how does it influence the output? Well, when somebody gives you a matrix and you decide on some series of operations, then there is an output which is defined, ideal output. But when you do it on computers, you get something slightly different. And the question is, how do we recognize it? By how much we missed? That's a good question. We don't really have tools yet. And that's the next lecture, actually. The next lecture, the main motivation is to get tools for analyzing situations like that. We don't have it yet, so let's try something else instead. Very often, when you have some object, like a matrix, there is a number which describes it in a certain way. And if you get lucky, this number is invariant, which means that it does not change when you are doing your tricks. Now, with elimination, there is a thing like that, almost, which is the determinant. When you are doing the row operations, these algebraic ones, you are actually not changing the determinant of the matrix. So here, this matrix and this matrix, they have the same determinant. And also these two matrices, they have the same determinant. Now, row flipping, this actually influences the determinant, but it only changes the sign. It does not change the magnitude of the determinant. How many row flips did we make? 1, 2. So it actually means that this resulting matrix has the same determinant as the original matrix. And this brings us to the first application of elimination. This is the most efficient way of finding the determinant of a really huge matrix. So what is the determinant of this original matrix? And the answer is, it's the determinant of this matrix. And because it is upper triangular, I just multiply the diagonal. So determinant of the original guy, I didn't give it a name, so let's wing it like that. The determinant of the original guy is the same as this determinant, which is 1 by 2 by 2, which is 4. Okay? Now, for us now, the important thing is that when we do these two operations, then determinant in absolute value does not change. So that's an invariant. When somebody gives me a matrix, this matrix has a determinant. And when I do elimination, ideally this determinant should not change in absolute value because there is no error of method. But because of numerical errors, it may change. And if you look at the change in determinant, it tells us something about the impact of numerical errors. Now, before we do some experiments, let's talk about it a little bit. Let's have a look at this guy here, number 2. How is it influenced by errors in the matrix, which happen at the start? So let's imagine that instead of -2, we have negative root of 2. I enter it into my computer, and the computer transforms root of 2 into a decimal number with an error. So there is a small error. Now, in the first stage, I use this as a pivot row, and I nicely spread the error all over the matrix in this column. So there is an error here now and also here. But perhaps there were also already some errors right at the start. This is also possible. In the second stage, I took this number, which already has perhaps 2 errors in it, and I still use it to modify this number. So these errors now are added to the errors which are already here. Now, if the matrix is larger, that this keeps happening. So this number, this poor guy, is loaded with all the errors from all the previous rows, essentially. So the original errors, they can accumulate really badly. The larger the matrix, the bigger the accumulation. So my guess, my feeling is that numerical stability of elimination is really, let's say, bad. And this is a very weak word. This looks like a potential for a catastrophe. This can be catastrophic. At least that's what my intuition tells me, that there can be really bad things happening when they are doing elimination. So let's test it. Here I have Maple, hopefully. And I have a little code here. So what am I doing? I decided to test 100 by 100 matrices. Why 100 by 100? Because I'm chicken and I'm worried to try something larger. I didn't test this computer for speed. And on my home computer, this could take about 3 seconds. So this can get easily out of hand. We will talk about it later. Okay, I am going to generate a random matrix, which is actually an integer matrix with integer entries. And I check that it's regular, because in numerical analysis, we do work with regular matrices. And then using some tricks, I'm not going to talk about them, I find the actual determinant. So this is a precise number. And then I transform this matrix into a floating point form, and I apply elimination, just how I explained it here. And I find the determinant of the resulting triangular matrix. And then I compare them, and this gives me the error. That's what's happening over here, and I actually find the relative error of the determinant. But this number does not tell us much by itself, because there is always some error present in our calculations, and this error depends on the precision of the underlying algebraic calculations. Every system has an error built into it. So what I do, I take this essential error, which is already in the system, which is unavoidable, and I divide by it the error which I get for the determinant. So the number which we will see at the end of the calculation is actually how many times the error of determinant, which is some way of measuring error of elimination, how many times it is larger than the usual error. And that's what's interesting, because it shows me how the elimination worsened the situation. So let me fire it up. 2, 3, 4 seconds. Okay, so that's an important parameter to keep in mind. So I see the number 8309. This tells me that after I used numerical elimination with floating point numbers on a 100 by 100 matrix, then the determinant had an error which was something like 8,000 times larger than the usual error of calculations. So the situation, the reliability of the answer of determinant is 8,000 times worse than I would expect for usual algebraic operations. By the way, let's recall something. When we have a relative error and we multiply it by 10, it means that we are losing one, let's say, reliable digit from the answer, one digit that we can reasonably trust. So the error is 8,000 times larger, which means I lost 4 digits of reliability. By the way, originally, I would trust something like 9 digits, because Maple by default works with 10 digits precision. Now, if I lose 3 digits or 4 digits out of 9, I'm losing essentially half of precision. This is really bad. This was just one random matrix. Let's try it again. And after about 4 seconds, we will see some other number, I'm pretty sure. And it's 48. So this wasn't so bad. Actually, the error is 50 times larger. This is bad. But compared to the previous example, this is actually quite nice. So you can see how everything is relative. By the way, we lost about 2 digits of precision, which is really bad. But as you saw, it can be much worse. This is an interesting message, which we will address it in the next lecture, that matrices differ in their, let's say, sensitivity or their fitness for elimination. Some matrices, they work with elimination really well regarding the numerical errors. Like this matrix. This is a good matrix, only 50 times larger error. So this matrix is good for elimination. The previous one was not very good. Okay, another 4 seconds. And let's see, 81. I mean, these are just random experiments, so we cannot really take away too much from them, but they do give us some feeling. 900, so we lost 3 digits of precision. You can see that the worsening of precision runs roughly between 50 and several thousands, 2,000, 3,000. So that's something to be expected, but for larger matrices, oh, 9,000, nice. For larger matrices, things could get much, much worse, but we don't have time for that, understandably, and you will understand more about it later. So let's cut down these experiments one more, just to give it a chance to surprise us. Once I got something like 4, which was very nice. 400. Okay, that's fairly standard. So we just confirmed by practical experiment that numerical stability of elimination is bad. And this can actually throw your calculations totally off, and you get something which is totally unreliable, and you just throw it away. So that's a big problem for real-life applications. Can we do something about it? The bad news is that we cannot avoid it. The good news is we can sort of restrict it. We can, with a bit of luck, make it much less fatal. How do we do it? Let's focus on one typical operation. We have some row, which is the pivot row. We called it K. And then there is some target row. Here is our pivot. And here we want to create 0 here, but we don't have it yet. Okay, that's row I. Now, let's imagine that there is some error in the pivot row. There is a number here, and it's the number plus some error. Now, when we are creating the 0 here, we take the pivot row, we multiply it by the constant Lik, which we can see over here, and we subtract it from the target row. So this error gets also multiplied by this constant Lik and is added to the target row to this particular place. So here we will get minus, we are subtracting, minus Lik times the error. So we can see that the number Lik, this coefficient, actually shows whether the error in the elimination gets multiplied or perhaps divided. The size of this number is very important for numerical stability. And when you think about it, you definitely want this number to be as small as possible. Now, what is this number? That's a good question. Lik. It's this number, Cik, divided by the pivot, Ckk. And we want this small. And it's crucial, so let me put exclamation mark here. That's what we want. How do we get small Lik's? The answer is by having really large pivots. So we want Ckk to be large. Do we have a choice? The answer is yes, we do. Let's have a look here. Our candidate for pivot was -8, but foolishly, being human beings, we replaced it with number 2, which was very convenient because we got nice coefficients for the operations. We did the same thing over here. But now we know that as computers, we would be worried about numerical errors, and we actually prefer really huge pivots. So we would keep this -8. Sure, what would be my L then? My L would be 2 divided by 8 is 1/4. So instead of multiplying every error by 4, I would be actually dividing every error by 4, which means that the situation would be 16 times better. When I'm a computer, I don't mind fractions. That's the beauty. So actually, this brings me to exams. On exam, when I ask you to show elimination in the standard numerical way, I actually don't expect you to also mimic the computer way by choosing the largest pivot, because I'm not sadist, and also I'm not masochist, because when you work with fractions, you start making mistakes, and then I have to find them. So there is a special dispensation that when you are on a test doing elimination by hand, you can actually choose small pivots, but that's very special, okay? In real life, in computer calculations, in applications, we always try to get the largest possible pivot by changing rows. So here, number 2, that would be a really good pivot. Here, number -8 also. This is called partial pivoting. Now, there's also something called full pivoting, as you can expect from the name, but let's not talk about it because it's a specific trick which is used quite rarely. Okay, so this is actually what is used most of the time, partial pivoting. Let me go back to the slide with algorithm. And this is actually what's in part 1. Part 1 is where we choose pivot. Okay, so when we pass to a certain stage, for instance here, stage 2, we are looking here at this column, we look at all the numbers and we choose the largest and by row flipping, place it here. So that's the contents of part 1, pivoting. And then we do part 2, which is the creation of zeros underneath the pivot. So now we see the whole algorithm in its entirety. And let's do some experiments, because I'm sort of suggesting here that partial pivoting should be beneficial. And we can try it out. So here is a new code. I create a random matrix and I make sure that it's regular. Then I find the actual value of determinant by, well, that's another story. I have some tricks for that and it takes time. And then I do 2 eliminations. One elimination does not do partial pivoting. It says pivoting minimal, it doesn't say pivoting none, because sometimes you do have to actually do some pivoting. If, when you go to a certain stage, you look here and you find 0. When you find 0 here, you cannot use it as a pivot, so what you do, you look down and you take something which is not 0 and flip rows. So that's, let's say, forced pivoting, something that you have to do in order to finish your elimination. And that's exactly what is meant by minimal pivoting, the least effort. If you don't have to, you don't pivot. Okay? And I find the determinant of the resulting matrix. And then I do partial pivoting, another elimination, and I compare the errors of these 2 outcomes of the determinant in absolute value. Okay? So I do 2 eliminations, one with pivoting, one without pivoting. For each of them, I find the determinant in absolute value, and I find the error of this determinant, and then I compare them. So the number that we will see is the error of elimination without pivoting, dividing by the error caused by elimination with pivoting. And let's see. Again, something like 5-6 seconds. Let's see, 3. Okay, this was fast. Number 48. This number 48 means that when we did not do partial pivoting, then the determinant had error something like 50 times larger. In other words, by doing partial pivoting, we actually cut down the error 50 times. So it is definitely worth it because we just gained 2 more reliable digits in our answer. And again, let's try to run it a few times to get some feeling for what the pivoting can do for us. Okay, improvement by 40. What's interesting, in theory, it's not guaranteed that pivoting will always pull the error down. It may happen that actually the error caused by elimination with pivoting will be even larger than elimination without pivoting, but such occasions are extremely rare, and in fact, in all my experiments, I never encountered it. I'm always getting numbers larger than 1 here. Now this is 164, so pivoting lowered the error 164 times, 50 times. So these are numbers which are somewhat lower than the numbers that we saw in the previous experiment. So this shows that we are actually not cutting down the error as much as we would want, which is what I said. I don't know how to solve completely the stability problem, but we are mitigating it, which is good. Now here I lowered the error only 7 times, which is good. I mean 7 times. But compared to previous runs, okay, it's not really so nice. But this could be caused, and typically this is caused by the fact that the random matrix which we generated is actually very nice. So even elimination without pivoting does not make such a huge error. And then, of course, there is no room for improvement. This can happen. Okay, so far we did not see any really huge improvement. I think the largest that we saw was something like 160. And again, this is caused by the fact that our matrix is relatively small, just 100 by 100. So one really cannot expect miracles, because also you don't get really huge totally insane errors for such a small matrix. But if we tried a matrix million by million, then we would see that pivoting really can help a lot. Well, we almost got the error 100 times, 75 times, which is very nice. I mean, these are really nice numbers. So that's partial pivoting. When you are doing some critical real-life application using elimination, if you don't use pivoting, you are making a huge mistake, okay? So partial pivoting is a necessary part of elimination and numerical analysis. 900, yeah, 900, so it's almost 1,000. So we cut down the error of elimination almost 1,000 times by using partial pivoting now, which means that we gained something like 3 digits of precision, which is very nice. Okay, one more chance to surprise us with some number, something which we didn't see before. I mean, 900, it was nice. 30, quite weak. Okay, that's life. So we just saw that partial pivoting is really important, necessary. And let's talk about, well, what was the next question that we asked? We asked about the error of method. That was easy. We asked about numerical stability, and it turns out that it's more interesting than in our previous topics. Nice. And that was it, usually. But today we have a new specific question. And this new question is about speed. We didn't ask about it before because it wasn't really crucial. It wasn't important. In real life, we do have to worry slightly about speed, but not that much with those previous topics, like Newton methods, things like that. For elimination, we do have to worry, because there are lots of calculations involved, and the good question is how many actually, because this tells us something about real-life performance. Before we get to theoretical answers, let me show you something. Here is an experiment. N is the size of a matrix that I'm going to eliminate. And I start with 100 by 100 matrices, which is exactly what we have been using here. Okay? I tried it at home on my computer. I generate randomly 10 matrices. I eliminate them, and I time it, each of them, and look at the average. So the average time of eliminating 100 by 100 matrix on my computer at home was 3 seconds. I think this computer is a little bit better. Okay. When I tried 300 by 300 matrix 10 times, it took 2 minutes. When I tried 500 by 500 matrix, it took 16 minutes. When I tried 1,000 by 1,000 matrix, it took 5 hours. Can you see the trend? Things are getting really bad really fast. That's why we need to worry about the speed of algorithm. How much work does it take to actually finish it? And, well, let me go to real-life applications. Million by million matrix is not surprising. This is actually still relatively small. So, how much time would it take my computer? How much time would my computer spend eliminating a million by a million matrix? I didn't do an experiment. You know why? I actually tried to fit a curve here to make a good prediction. And I used some theoretical knowledge for that. We will soon get to it. And the estimated time is 100,000 years. Now, in all these previous experiments, I would make actually 10 experiments and take the average. 10 experiments took 3 days. I couldn't play games for 3 days. That was really... Okay, let's not talk about it. Anyway, I did not do this experiment. You can see why. And that's the reason why one has to be careful here at school, if I don't really know the system, in judging what kind of matrices I want to use in my examples. If I tried 300 by 300 matrix here in my examples, those examples would take, this one is slightly, okay, 1 minute. We would be waiting 1 minute for each result in our experiments. So This shows that speed is a very big concern for elimination. It's a new question, we didn't have it before, and we have to really look at it closely and hard. So let's make some room and let's address this question. Here we go. When you start the program and you are interested in how long it will take for the program to finish, then in numerical analysis, typically the most important factor is the number of algebraic operations that you have to perform. And in the scientific language, this is called computational complexity of an algorithm. So what is the computational complexity of elimination? How many operations I have to perform, basic algebraic operations, to get from the original matrix to the triangular form? Now, in general, in numerical analysis, typically we have a matrix which has a square matrix as its core. So I imagine a square matrix. Do I want to write? Okay, let me put just a few numbers. A11, A1n, AN1, ANN. The important thing is that it's n by n matrix. And then sometimes, very often, almost always, we add some extra columns. So when we are solving a system of equations, we add another column. We may be solving simultaneously 15 systems of linear equations, then we add 15 columns, and so on. We use elimination to find inverse matrix. How do we do it? Well, we attach identity matrix. So we attach n columns, and so on. So typically, there would be c columns also attached on the right. So that's the matrix that we start with. And we also can assume that this square matrix, which is the core of this matrix, is actually regular. So we always find good pivots, everything works well. And the aim is to transform this matrix using elimination to a new matrix where this core part, the square part, will be upper triangular. That's what we are trying to achieve with elimination in general. How do we do it? Well, we go column by column. So let's imagine that we already fixed several columns. So we have zeros here, underneath the first pivot, and so on. So some part is already done with zeros here. And finally, we are getting to the place where we ignore several columns, we ignore several rows, and there is a pivot. And we are looking at it and thinking, okay, we need to create zeros underneath this pivot. Now, typically we would use k for the pivot row and pivot column. But this would lead to calculations that are a little bit more difficult than is necessary. So it will be more convenient if I call by k the number of zeros which I want to create. So here I need to create k zeros. And because this is a square matrix, this core, it means there will be k extra columns here that I have to handle, and also c columns here. And this in turn means that actually the dimension of this matrix, including the pivot row, is k plus 1. But we will not need it, okay? So that's the setting for my exploration. And I ask, how many operations do I have to make in order to create zeros below the pivot element? We do not worry about exchanging rows because this is typically handled just by changing pointers, okay? So let's ignore partial pivoting. We already do have the right pivot. We are creating zeros. So first of all, we have to create zeros for k rows. So it means something will be done k times. Now, what will be done for each specific row? Let's see. How do we do this elimination business? Well, first, we look at the number below the pivot, and we find the coefficient Lik. How do we find it? Well, we divide this number by the pivot, this number by the pivot, and so on. This is one operation, one division. So this division finds Lik. Now this is different k from this one. Okay? Slight abuse of notation. After we find this k, we start doing the parallel operations. Now, how many of them do we have to make? First of all, this 0 here can be done without any calculation at all, because if you calculated L properly, then this will be 0. You just put it there. So what we really do, we are calculating new numbers in the other columns. So how many numbers do we have to calculate when we are doing a specific row? We have to go from here, keep subtracting. So there will be k numbers that we have to fix, but also c numbers that we have to fix. So that's k plus c numbers that we are changing. And how are we changing those numbers? Well, let me do a little return to our favorite slide. How do we replace numbers? Well, we can see the formula there. We take the number in the pivot row, multiply it by this coefficient L, and subtract. Multiplication, subtraction. 2 operations, that's it. Let's think about it. For each row, we find the coefficient, and then we handle all the other columns. Yeah? This seems to work. So this is the number of operations that we need for a specific stage. Now, this is typically floating point operations, which are a specific kind of operations. So people use the shortcut flops, which is funny. Anyway, so we need this many flops for one stage. How many operations do we need for the whole elimination? Well, we have to sum up the operations needed for each stage. By the way, notice that this is a pessimistic number, because when you get lucky, there will be already some zeros present in the matrix at the right time, at the right place. So you could save perhaps some operations, but you don't know, so we have to be pessimistic here. Okay, we are summing up this number. Let me rewrite it in a nicer form. So it's k plus 2k squared plus 2ck. What are the k's? Well, k told me here how many zeros I have to create. The smallest possible number of zeros I have to create is 1. That was the last stage. I was creating just 1 0. So k runs from 1 all the way up to the largest possible number. The number of rows is n, so the largest number of zeros to create is n minus 1. Here we go. So this is the answer, but let's look at it closer, because of course you don't see anything from this number. It's not exactly the form that we would like to see at the end. So how do I want to play with it? Okay, let's break it up. Let's break it up into 3 sums. Let's start with the highest power for k. Then we've got summation of k's. And then we've got 2c times summation of k's. Perhaps we could put this together, doesn't matter. Okay, I've got 3 sums, and let's jot our memory a little bit, okay? So if I visit the sediments in my memory bank somewhere down, among this mud and things like that, I can see some formulas for summation of k's and summation of k squared. Yeah, I could have factored out too. Okay, doesn't matter. Yeah, let's do it. I think it will be better. Let me put the 2 here. So when I was in high school, they actually forced me to memorize the formula for the summation of numbers from 1 to n. That's what I learned. And they were really hard on me. I really had to memorize it well, so I still remember it. n by n plus 1 divided by 2. Okay. Now, my summation here stops 1 short. So instead of n, I have n minus 1, which means that I should be using n minus 1 by n divided by 2. That's what should come here and also here. By the way, when n is really, really, really huge, this is about n squared over 2. And that's very convenient when you are analyzing algorithms, actually. If I wanted, I could, instead of equality, I could put this asymptotic equality. It would simplify my life. But let's do precise calculation, just for the fun of it. Okay, something here, twice, plus this formula, n minus 1 times n over 2, plus 2c times n time, okay, I switched it around, doesn't matter. Okay, here we go. The summation for k-square, that's a little bit less popular, and many people don't actually remember it, which is okay, I don't mind. But I was forced to memorize this one too, and I remember it slightly less, I have to admit, but I still do have something in my memory. Let me see. N by n plus 1 by 2n plus 1. Is that it? Yeah, I think that's it. So I take it now, and I move n to n minus 1. So the n minus 1 version would be n minus 1 times n times, and let me think about it. I don't want to make a mistake here, because if I do, I have to redo all the calculations. Yeah, this is a let's say, touchy moment for me as a lecturer. I have to be very careful not to make a mistake here, and sometimes I do. Okay, I take this n, and I replace it with n minus 1. So it becomes 2 times n minus 1 plus 1, which is 2n. Minus 2 plus 1 is minus 1. Okay, that's the number which comes here. 6 n minus 1 and 2n minus 1 it was, I think. Okay. Let's have a look at the outcome and write it in some nice way. Okay, I can see 1/3. And let's multiply out. Okay, there is this n. I put it out, and I just multiply out the two brackets, and then I sort of put the n back. So I ignore it. I'm multiplying out, and I can see 2n squared, but it's actually 2n cubed. I'm putting it back, this n. Minus 2n, minus n is minus 3n, and I put this one into it, so it's square. Minus 1 by minus 1 is plus 1, plus n. Okay, so far so good. Plus 1/2 n squared minus n plus c times n squared minus n. Okay, how do I put it together? Let's see. I keep the c guys away, and I will put these two polynomials together. So n cubed is the boss here. How many times? 2/3. That's a good news, because I remember that this one is correct. 2/3 n cubed. Minus n squared plus 1/2 n squared is minus 1/2 n squared. Third of n minus half of n. Third minus half. It's 6, 3. It's negative 1/6n. And that's it, hopefully. Plus cn squared minus cn. Okay. Let's see. Where do I hit the right target? Crossing fingers. 2/3 n cubed. Cn squared, I can see it there. Minus 1/2, I can see there. Minus cn minus 1/6. Yeah. Sigh of relief, good. So I don't have to do it again. I managed to do it at the first try. Okay, let's talk about it. In numerical analysis, n can be really, really, really huge. And therefore, when I'm comparing these powers, n cubed is dominant, definitely. And these two guys, they can be ignored. How about cn squared and so on? Well, n squared is negligible compared to n cubed, but how about this c? And that's a good question. For instance, when you are finding inverse matrices, then c is actually equal to n, and suddenly you have another n cubed in the game. So I cannot just cross it out. I can cross out this one, because it's negligible compared to this guy. So there are actually two candidates for the boss position. Let's go back to our original motivation, solving systems of equations. If you are solving systems of equations, then c is equal to 1, and this guy can be also ignored. So that's the special form that we can see as a corollary. When you are solving system of equations or doing something comparable, like finding determinant, then c is equal to 0. Wonderful. Then elimination can be expected to take 2/3 n cubed operations. Okay, good news, bad news. As far as algebra, as the theory of algorithm goes, polynomial computational complexity is considered the best case, okay, or the second best case. There are definitely worse things. It could be factorial or it could be an exponential. These are really bad algorithms. So this is actually considered to be the best group of algorithms, polynomial algorithms. Very nice. Now the bad news. Although it's the best group, in real life, n-cube can be really, really bad. Okay? We saw it. We saw the chart. Okay? Let's have a look at it in this way. What happens if you decide to double the size of the matrix? How does it influence the runtime of your computer? The answer is if you double the size of the matrix, then this 2 will become cubed, and the time requirement is multiplied by 8. So every time you double the matrix, you can expect the algorithm to run 8 times longer, which is quite a lot. Now, if we somehow recall from memory the chart that was here, if you rewind the video, you can see that it actually does not quite work because there are also other factors. For instance, memory management. And these things can also blow up things. They definitely do not get them shorter, but they can, make things run longer. And this happened when I was testing my computer. After my matrices exceeded a certain size, then it was much harder for the computer to actually handle the memory management. So actually, the runtimes got even longer, even worse than this. So this is actually still optimistic. In real life, you can expect even a little bit worse. So this is a really bad news. And it shows that elimination for huge systems can be a problem. Okay? Now you may say, okay, I buy a better computer. Now recall the chart. For 100 by 100 matrices, it took 3 seconds, and so on. For million by million matrices, it took 10 to 5 years. So let's say that you buy a computer which is 100 times faster than my computer. Is it possible? Yes. Will it cost you? Definitely, because 100 times faster. This is already not cheap. So you get a 100 times faster computer, and still the calculation, the elimination of a single million by million matrix would take 1,000 years. Okay? So going after speed using brute force, using hardware, can be extremely difficult, extremely expensive. Now, there are ways, there are situations when you simply don't have an alternative. So, yes, sometimes you do have to use elimination for large matrices, and yes, you suffer. But this is a clear-cut motivation to find different ways to solve systems of linear equations. And we will do it, and 2 videos from now, there will be a totally different attempt, totally different approach to solving systems of equations, okay? This is a clear-cut motivation. But sometimes we do have to use elimination, and now we have 2 important messages. Message number 1, use partial pivoting, otherwise you cannot trust the answer at all. And message number 2, be careful about using elimination. It takes a lot of time, okay? And if you need to use it for huge matrices, be prepared to invest heavily from your pocket. Okay, so much for elimination. Is there anything else we can talk about? I don't think so. I actually think we essentially covered it all. So let's return back to our original question. How do I use elimination to solve specific problems? Okay, we already saw that it can be used to find determinant, and this is a definitely good application, but of course there is more to it. Okay, here we go. A system of linear algebraic equations. The matrix A is square and regular. We want to find a solution efficiently for huge matrices on a computer. So we talked about it, specific situation. Now, how do I find a solution using elimination? When I go back to high school, it actually worked like that. I would form an extended matrix by taking A and attaching B. And then I would do elimination. Now, it would be a different elimination because when I was going through those stages, when I was at a specific stage, they would actually teach me to create one for pivot by dividing the rows, which we are forbidden now, but let's stick with it, okay? So by dividing the row, I can actually achieve the pivot to be 1, and then I was actually asked or told to create zeros also above the pivot, not just below, above the pivot. And keep going, and eventually I would arrive at the identity matrix, and here on the right I would find a solution That's what I was taught when I was in high school. Now, this approach is, I mean, it's not wrong, definitely not. And it does not really have an official name, but many people call it the Gauss-Jordan elimination method. Sometimes the shortcut GJM is used. But anyway, Gauss-Jordan, actually, Jordan didn't invent it either. So both names are actually there in the title of the method by mistake. Funny story. Anyway, so this is what they taught me in high school, but how does it work? How does it fit with my numerical elimination? Well, here is the story. This algorithm, of course, can be described, and if you are curious, you can find it in the notes, in the lecture notes. But the important thing is, you can do the analysis of computational complexity, and when the dust settles, you find that this type of elimination requires n-cube operations. Now, in the theory of algorithms, we do not really care much about the constant in front of the power. So we would say that this elimination and the Gaussian elimination, the numerical one, they are comparable. But if you have to wait for 10,000 years, you definitely don't want to add half as much to your waiting time, okay? Okay, so let's say that you heavily invest in a computer, and this numerical elimination would last just 1 year. But if you use this one, it would last 1.5 years, okay? So this constant does matter. Here it's n cubed, but the numerical Gaussian elimination just had 2/3 n cube. So that's why we don't use it. We don't use this approach because we do not like n cube. And that's why I do not want to spend too much time on it, okay? So this is just buried now, okay? As of now, this is gone. What we do instead, we take the matrix A, attach the right-hand side column B, and we use the standard numerical elimination, which has requirement on our time or on our operations 2/3 n cube, which is significantly less than this high school way. And it brings us to a specific situation. We have an upper triangular matrix and some vector on the right. So regarding the time that you spend on it or the number of operations that you have to perform, this is much superior, significantly superior. However, you do not get the solution at the end. That's a little problem. So how do we handle it then? Well, let's have a look at an example. This is not a matrix of a system because it's just a square matrix. So let me pass to a modified example where I copy the original matrix to -6, -2, 1, 1, 0, -2, 0, 1. And I attach a column, 0, 1, -1. Okay, and now I'm going to eliminate this matrix. However, notice that when I'm doing elimination, I'm working just with the first 3 columns because then I get the right shape. I do not really care about the last one. I mean, I do care, but it does not influence my decision making. That's the key part. All the decisions which I did over here will be also done over here. So I will do exactly the same operations which I've done over here. And therefore, the resulting matrix will have exactly this form, the form that we arrived at before. And if I want to know the outcome of elimination applied to this matrix, I just need to figure out what to do with the right-hand side column, and I can actually see it in my list of operations, which is the reason why I preserved it. So the first operation I did was flipping of the rows. 1, 0, -1. Then I subtract the first row twice from the second. I can actually read it in those coefficients L, I, K. I will be talking about them soon, important things. So twice. I take the first and take it twice from the second. I take the first and add it twice to the second. Then the next operation is flipping the second and the third row. And in the last step, I am adding 4 times the second one to the third one. And that would be here. So if you don't trust me, take this matrix as a unit, as a whole, and apply elimination to it with the same decision making, the choice of pivots, and you arrive at this matrix. Okay, this is an interesting lesson. We will return to it later. Okay, so this is our example. I took the matrix of the system, I applied Gaussian elimination, which is more efficient than the high school trick, and I arrived at a matrix which is upper triangular, and then there is some vector y on the right. So how do I get to the solution? Let's have a look at it. This actually is a matrix of some system. How does the system look like? X plus y is equal to 1, 2y plus z is equal to 1, 2z is equal to 2. When you look at a system like that, it's a triangular system, and you think, okay, wait a second, I can right away figure out how much is z. Now, we see it, but let me write it. It's 2 divided by 2, which is 1. How many operations did I need? One operation. What if the system were different? I would still need one operation. Because if a system is triangular, the last equation must look like this. Number times z is equal to number. So, one operation. Okay, I know z, and I can go up by 1. If I know z, then I can figure out y as 1/2 of, I take the right-hand side, and I subtract z. But in general, there could be a number here. This time the number is 1. 1 times z. So let me write it. It's 1 times 1. Okay, how much is it? 1 minus 1, it's 0. Key question, how many operations did I need? The answer is, okay, there is this division, one flop, and there is something more. Here I had to get rid of the variable which was already known from the previous stage, and this took 2 operations, 1, 2. Altogether 3 floating point operations. Okay, we know z, we know y. Okay, let's go up. How much is x? X is, okay, I imagine that there is a number here. So it's 1/1. 1 minus, I have to get rid of y, which is taken once, and I have to get rid of z, which is taken 0 times. Okay, of course I wouldn't do it like that if I just wanted the answer, which, by the way, happens to be 1. But I'm really interested in the number of operations. And you can see that compared to the previous calculation, there is this division, which is the 1, which was also here. The division is there. And then we keep adding groups which needs to be factored out, which needs to be got rid of. And each group takes 2 operations to remove. So this will be 5 floating point operations. And if I had a 4x4 system, there would be another equation here, and it would need 7 operations, and so on. So first of all, this is an algorithm. This is called back substitution because we are going backwards. For upper triangular system, backward substitution gives you the answer right away. You don't need to do some eliminations or manipulations, anything. You simply have explicit formulas, and you just go through them. So this is very efficient, very nice from the programming point of view, because you have formulas. Here, you can see them in the long form, and here you can see them in the shortcut form. So it's essentially just a matter of 1 or 2 cycles, depending whether you understand summation as a cycle or not, essentially. Nothing more to it. So this backward substitution is a very efficient way to solve upper triangular systems. And you get a solution. Here you go. Now, how much work does it take? That's important because we are trying to do some savings compared to the high school approach. Okay, so how many operations did we make? 1 plus 3 plus 5. If the system is larger, we have to make more back substitutions. So we are adding odd numbers. How many of them? Well, it's the same as number of equations. We are adding n odd numbers. And there is a formula which is fairly simple. It's n square. And there is nothing which we ignore. This is precise number, n square. We don't have to worry about some ON or something like that. Now, I need specific number of operations for elimination, n cubed times some constant, and I need n square operations for the back substitution. N square is negligible compared to n cubed, which means that the grand total is still 2/3 n cubed. So we are saving time compared to this high school approach with unit matrix. Definitely, in applications, you want to go for upper triangular matrix and then finish it off with BS, with backward substitution. That's the preferred way. Incidentally, let me confirm it. The same thing can be done for lower triangular systems. When you have a lower triangular system, we will get to it, you can do substitution as well, but you start from the top and you go down. So that will be the forward substitution, okay? And both of them are essentially done by the same mechanism. So both of them, here is the confirmation, both of them have time complexity or computational complexity n square. And I think I have the definition of the lower triangular system forward substitution over here. So that's just for the sake of completeness. You can imagine how this definition goes for the forward substitution. Okay, so this is the situation. We don't want to use this identity matrix business. We definitely want to go this way. Let's try it out. So this is just a simple example to show how things work. I have a 4x4 matrix, right-hand side column, and now I do the standard high school way of solving it. So I used elimination, and my specification for the output was Gauss-Jordan, which is the name, as I said, for it. And I can see on the output identity matrix, and on the right, the column of solutions, 2, 0, negative 2, 1. And now, let's try something else. First, I take the extended matrix, and I apply the elimination, but the numerical version. And the outcome now is upper triangular matrix, and some vector on the right, okay? And then I apply back substitution to this triangular system, and I get 2, 0, negative 2, 1, which is the same as what I obtained using the high school approach, okay? Let's have a look whether it really pays off. So what I have here is a comparison of runtimes. I got daring when I was trying it at home, so I'm increasing the size of the system to 150, so that you can see something more substantial. I generate a random system, and then I solve it two ways. One way is the high school Gauss-Jordan with unit matrix, and I time it. And then I try elimination, the numerical way, and back substitution. And again, I time it, and we will see comparison of times. So here we go. This time it will be longer. This one took 5, yeah. So 6 seconds for this, and 2 seconds plus 0.1 second for this one. Now, what is really strange that the Gauss-Jordan method should be slower only by about a half. So I would expect something like almost less than 4 seconds for the GJM, but it's significantly more because there's also there are more things happening with memory management, things like that. So in reality, it's even slightly worse, very, very often, okay? But this is a typical situation. If I run it again, I expect to see similar numbers, something like 6 seconds. Yeah, here we go, and Gauss elimination. Let me just out of curiosity switch these two, because that's also something which may have an impact on the numbers. So in order to be fair, first I'm going to do the numerical way, and then I go the high school way, and we will see what the numbers will be. Because this is another factor in real-life computing, so there are factors which have to be taken into account, and you can see now that the numbers are different. So when I'm starting this, then the computer has to do some memory management things which slow it down. And the first method which I use actually seems to last longer. You can see it now. Previously, the elimination took about less than 3 seconds. Now it's 3.5. And the Gauss-Jordan previously took about 6 seconds, and now it takes less than 5. So you can see that actually the previous experiment was really bad for the high school way. It wasn't fair to it, but now it is fair and it's still worse. Okay? And you can still see that the Gauss elimination takes 3.5 seconds, which is definitely less than Gauss-Jordan method. And you can see that it's much more than the back substitution, which is really negligible. You can see that this n square negligible compared to n cube. You can see it here with your own eyes. Now I'm going to get daring, and I'm going to put 250. Oops. Okay, 250, which is almost twice as much, which means it will run. Okay, 8, 3, 20, half. It will take about less than a minute, I think. That's my estimate. So I'm going to run it and talk a little bit about things, and then we will look at the answers. Okay, here we go. So let's talk about things. This is how I learned it in high school. Okay, you go and you are creating ones on the diagonal and zeros elsewhere, column by column. There is an interesting twist. What you can do, you can use Gaussian elimination to obtain upper triangular matrix. And after you obtain it, you can now start creating ones on the diagonal and zeros above them, but you go from the back. So you create 1 and zeros, 1 and zeros, and you go backwards like that. And eventually you end up with identity matrix and the actual solution. And you find that when you are doing this backward step, this takes n square operations, and this of course takes 2/3 n cube, because that's the ordinary elimination numerical. So actually you can get identity matrix as efficiently, at least regarding the number of operations, as this recommended procedure. But this is not how it is taught in high school. And secondly, you will find that when you are going backwards, you're actually doing exactly the same calculations, but you're doing them in chunks, part by part. You are not doing them all at once. And you are storing the intermediate steps in the memory. You keep changing the right-hand side column repeatedly. So from the practical point of view, this is also rather inefficient. It's not as inefficient as this approach when you're doing column by column. This is much superior, but it's still worse than a backward substitution approach. So we definitely want to do it like that. However, when you are doing just a small system by hand, this is actually a very useful observation. So when you are solving a small system 3x3, 4x4 by hand, the really superior way to do it may be that you go for upper triangular matrix, and then you start creating ones and zeros above, step by step, going backwards. This is also fairly good for small systems done by hand. Okay, but I don't want to see it here in real-life numerical calculations. This is the preferred way. Do we see some answers? Yes. Well, okay, let's have a look at it. Elimination took 11 seconds. Backward substitution, half a second, so it's negligible. So let's talk about 11 seconds for this recommended method. And the identity high school approach, identity matrix, took 21 seconds. Yeah, I think it's clear which way we want to go. Okay, so now we know how to solve systems of equations efficiently. Elimination with partial pivoting, definitely, leading us to upper triangular, and then, bang, we go for the solution using back substitution. By the way, one interesting question is how to find an inverse matrix. And what we learned in high school was that we should attach identity matrix next to it and do the high school elimination so that there is a unit matrix on the left. But now we know that perhaps there might be a better way. And indeed, what you do, you change the system using numerical elimination into a system which has on the left an upper triangular matrix. And then you just treat this as n independent systems of equations, and each of them you can solve using back substitution. And then you take the results and you compose them together and you get the inverse matrix. And when you do it like that, you actually save 1/3 n cubed. That will be the savings. Just like we saved 1/3 n cubed here, okay? So it's comparable. Also, the inverse matrix can be found using backward substitution. Okay, so we have a numerical procedure for solving systems of linear equations using Gaussian elimination, numerical version, and back substitution. Let's ask some good questions. For instance, numerical stability. How sensitive is this procedure to numerical errors in elimination and in back substitution as well? But this is not really a big problem, this back substitution. Okay? And we have some answers. We talked about partial pivoting. So good question is, will it also help us with reliability of the solution? Let's try some experiments. Here we go. I'm going to generate 200 by 200 systems. So I'm really getting daring now. It could take about 8 seconds, I think. I'm estimating based on the previous experiments. So in about 8 seconds, we should be able to eliminate the system that we create. And again, I'm going to do 2 eliminations, one without pivoting, one with pivoting. I find the solution using back substitution. Look at the error of this solution, and I compare again the errors of the version without pivoting and with pivoting. So the number that we will see will be the number how many times pivoting improved reliability, essentially. Here we go. So let's see. 2, 3, 4, 5, 6, 7, 8. It's getting long. Okay. So the ratio of errors, that's what I want to see, is 135. So for this particular system, which we do not see, it's generated somewhere in the background. It's a big system, 200 by 200. For this particular system, if I apply partial pivoting, it will cut down the error 135 times, which means 2 digits of precision out of 9 were saved. I think it's worth it. Okay, let's try it a few more times. 2. So it takes about 6 seconds, the elimination, it seems. Here we go. Improvement 42 times. Okay, it's not really a big hit, but yeah, 40 times, it's good. So another 6 seconds, and we will see, 800. Now, that was nice. And again, one of the reasons why we see numbers that differ quite a lot is that some matrices are more sensitive and some are less sensitive to errors in elimination. We will talk about it in the next lecture. So right now we are just observing the effects, okay? So sometimes there is not much room for improvement because the matrix is very nice, not making errors. But this looks like a matrix which is sort of like sensitive to numerical errors. So the version without pivoting was really, really bad. And pivoting had some room to improve. 3 digits of precision just saved. Okay, I've seen all kinds of numbers here at this stage when I'm running it. I also tried it at home many, many times. And I could get as high as 10,000 actually. I got lucky or unlucky, it depends. Wow, ratio of errors, 13,000. We got lucky. Wow, we've got ourselves a winner. So this time, pivoting decreased the error 13,000 times, which means it saved 5 digits of precision out of 9. So the original matrix must have been totally dreadful. And if I used elimination without pivoting, then the answer was good for essentially nothing. I could just throw it out. Okay? So we will talk about it. One has to be really careful with elimination, with reliability. Okay, so pivoting is definitely worth it. Let me show you one extreme case. And this is actually a very simple case. I don't need any matrices of crazy size. This is a 2 by 2 matrix. It's a tiny system. Okay, a very simple system. Right-hand side 1, 2, which is also nice. I'm going to try elimination without pivoting and with pivoting. Without pivoting, the solution reads 0, 1. With pivoting, 1, 1. Which one is right? The answer is, of course, the second one. You can see that when I didn't use pivoting, I didn't just make a small error. I actually made a significant error because these two vectors, they are very distinct at the first sight. So you can see that pivoting can be very helpful, and you can also see that if you don't use it, you can really have significant errors. This example actually is nice because I can explain to you, I can show you how these things work. I have a very small number in the upper left corner. And I have ones elsewhere. And it's actually not difficult to solve it explicitly, and you find the answers. You find a solution. And of course, I don't remember it by heart, and I'm not going to solve it here because it would waste time. So let me copy it from my notes. So x is 1 over 1 minus epsilon, which is essentially 1, because epsilon is really tiny. And y is 1 minus 2 epsilon divided by 1 minus epsilon. And again, epsilon is very tiny, so this is essentially 1. Okay? So the solution is almost 1, 1. Now, here comes the interesting part. What happens if you try to eliminate without partial pivoting? You keep it like that, although epsilon is very tiny. Partial pivoting would force you to switch the rows. But if you don't apply it, you have epsilon here. And now, how do you get 0? You have to divide the pivot row by epsilon and subtract. And you get 0. Here, you divide the pivot row by epsilon and subtract. Here, you divide by epsilon and subtract. Now, this is theory. Let's have a look at real-life result in computer. Now, epsilon is a very tiny number. It's 10 to negative 11 in my example. So when I do 1 minus epsilon, I get 10 to 11. So this number is 10 to 11, and I subtract 1. The problem is, Maple only works with 10-digit precision. This is a small number, but Maple can keep it, because it's 1 times 10 to negative 11. No problem in keeping such a small number. But when this small number meets a large number, we start having troubles. So for Maple, this one here is irrelevant. 1 over epsilon is a huge number, 10 to 11, you can see it, 10 to 11. So this is essentially just 1 over epsilon with negative sign. For Maple, this one disappears. And the same thing happens here. And you can see the problem now, because this is an upper triangular system. I use back substitution, and I find that y is equal to 1. And then, when I go on, and I do the back substitution, things like that, I arrive at x is equal to 0. Because 1 here, I subtract, and I get 0. Okay? You can try to play with this system when you flip the first two rows, and you do the elimination, and you apply reasoning like that the computer cannot really match a huge number with small number, and you end up with a much nicer situation where you actually get the solution 1, 1. Okay? So this was a real clear-cut warning that partial pivoting is crucial also for solving systems of equations.